Hey guys, how's it going? Let me continue the book on page 80. 4.4 External Variables. A C program consists of a set of external objects, which are either variables or functions. The adjective external is used primarily in contrast to internal, which describes the argument and automatic variables defined inside functions. External variables are defined outside any function and are thus potentially available to many functions. Functions themselves are always external, because C does not allow functions to be defined inside other functions. By default, external variables are also global, so that all references to such a variable by the same name, even from functions compiled separately, are references to the same thing. In this sense, external variables are analogous to Fortran, common, or PL/I external. We will see later how to define external variables in functions that are not globally available, but are instead invisible, but are instead visible only within a single source file. Because external variables are globally accessible, they provide an alternative to function arguments and return values for communicating data between functions. Any function may access an external variable by referring to it by name if the name has been declared somehow. If a large number of variables must be shared among functions, external variables are more convenient and efficient than long argument lists. As pointed out in Chapter 1, however, this reasoning should be applied with some caution, for it can have a bad effect on program structure and lead to programs with many data connections between functions. The second reason for using external variables concerns initialization. In particular, external arrays may be initialized, but automatic arrays may not. We will treat initialization near the end of this chapter. The third reason for using external variables in their scope and lifetime automatic variables are internal to a function. They come into existence when the routine is entered and disappear when it is left. External variables, on the other hand, are permanent. They do not come and go, so they retain values from one function invocation to the next. Thus, if two functions must share some data, yet neither calls the other, it is often most convenient if the shared data is kept in external variables rather than passed in and out via arguments. Let us examine this issue further with a large example. The problem is to write another calculator program better than the previous one. This one permits plus, minus, multiply, division, and equal to print the answer. Because it is somewhat easier to implement, the calculator will use refers Polish notation instead of infix. Reverse Polish is the scheme used by, for example, Hewlett-Packard Pocket calculators. In reverse Polish notation, each operator follows its operands. An infix expression like is entered as parentheses are not needed. The implementation is quite simple. Each operand is pushed onto a stack. When the operator arrives, the proper number of operands, 2 for binary operators, are popped. The operator applied to them and the result pushed back onto the stack. In the example above, for instance, 1 and 2 are pushed, then replaced by their difference, -1. Next, 4 and 5 are pushed, and then replaced by their sum, 9. The product of -1 and 9, which is -9, replaces them on the stack. The equal operator prints the top element without removing it. So, intermediate steps in a calculation can be checked. The operations of pushing and popping a stack are trivial, but by the time error detection and recovery are added, they are long enough that it is better to put each in a separate function than to repeat the code throughout the whole program, and there should be a separate function for fetching the next input operator or operand. Thus, the structure of the program is: the main design decision that has not yet been discussed is where the stack is. That is, what routines access it directly. One possibility is to keep it in main and pass the stack and the current stack position to the routines that push and pop it. But main doesn't need to know about the variables that control the stack. It should think only in terms of pushing and popping. So we have decided to make the stack and its associated information external variables accessible to the push and pop functions, but not to main. Translating this outline into code is easy enough. The main program is primarily a big switch on the type of operator or operand. This is perhaps a more typical use of switch than the one shown in Chapter 3. So much words. A long sentence. This code is too long. The command C clears the stack with the function clear, which is also used by push and pop in case of error. We will return to getTop in a moment. As discussed in Chapter 1, a variable is external if it is defined outside the body of any function. Thus, the stack and stack pointer, which must be shared by push, pop, and clear, are defined outside of these three functions. But main itself does not refer to the stack or stack pointer. The representation is carefully hidden. Thus, the code for the equal operator must be used to examine the top of the stack without disturbing it. Notice also that because plus and multiply are commutative operators, The order in which the popped operands are combined is, is irrelevant, but for the minus and divide operators, the left and right operands must be distinguished. Exercise 4, mid-score 3. Given the basic framework, it is straightforward to extend the calculator, add the modulus percent and unary minus operators, add an erase command which erases the top entry on the stack. Add commands for handling variables. 26 single letter variable names is easy. 4.5 Scope rules. The functions and external variables that make up a C program need not all be compiled at the same time. The source text of the program may be kept in several files, and previously compiled routines may be loaded from libraries. The two questions of interest are hard declarations written so that variables are properly declared during compilation. Hard declarations set up so that all the pieces will be properly connected when the program is loaded. The scope of a name is the part of the program over which the name is defined. For an automatic variable declared at the beginning of a function, the scope is the function in which the name is declared, and variables of the same name in different functions are unrelated. The same is true of the arguments of the function. The scope of an external variable lasts from the point at which it is declared in a source file to the end of that file. For example, if file sp, push, pop, and clear are defined in one file, the order shown above, that is, then the variables file and sp may be used in push, pop, and clear simply by naming them. No further declarations are needed. On the other hand, if an external variable is to be referred to before it is defined, or if it is defined in a different source file from the one where it is being used, then an external declaration is mandatory. Then an external declaration is mandatory. It is important to distinguish between the declaration of an external variable and its definition. A declaration announces the properties of a variable, its type, size, etc., etc. A definition also causes storage to be allocated, even if the appear outside of any function. They define the external variables sp and val cause storage. va1 cause storage to be allocated and also serve as the declaration for the rest of the source file. On the other hand, the lines declare for the rest of the source file that sp is an int and that va1 is a double array. Whose size is determining elsewhere. Whose size is determined elsewhere, but they do not create the variables or allocate storage for them. There must be only one definition of an external variable among all the files that make up the source program. Other files may contain external declarations to access it. There may also be an external declaration in the file containing the definition. Any initialization of an external variable goes only with the definition. Array sizes must be specified with the definition, but are optional with an external declaration. Although it is not a likely localization for this program, figure1 and SP could be defined and initialized in one file, and the function push, pop, and clear defined in another. Then these definitions and declarations would be necessary to tie them together. Because the external declarations in file 2 lie ahead of and outside the three functions, they apply to all. One set of declarations suffices for all file 2. For larger programs, the hash include file inclusion facility discussed later in this chapter allows one to keep only a single copy of the external declarations for the program and have that inserted in each source file as it is being compiled. Let us now turn to the implementation of getTop, the function that fetches the next operator or operand. The basic task is easy. Skip blanks, tabs, and new lines. If the next character is not a digit or a decimal point, return it. Otherwise, collect a string of digits that may include a decimal point and return number. The signal that a number has been collected. The routine is substantially complicated by an attempt to handle the situation properly when an input number is too long. getTop reads digits, perhaps with an intervening decimal point, until it doesn't think anymore, but only stores the ones that feed. If there was no overflow, it returns number and the string of digits. If the number was too long, however, getTop discards the rest of the input line, so the user can simply retype the line from the point of error. It returns too big as the overflow signal. What are gauge and n-gauge? It is often the case that a program reading input cannot determine that it has read enough until it has read too much. One instance is collecting the characters that make up a number until the first known digit is seen. The number is not complete, but then the program has read one character too far, a character that it is not prepared for. The problem would be solved if it were possible to unread the unwanted characters in every time the program reads one character too many. It could push it back on the input, so the rest of the code could behave as if it had never been read. Fortunately, it is easy to simulate and getting a character by writing a pair of cooperating functions. Gauge delivers the next input character to be considered. Engage puts a character back on the input so that the next call to Gauge will return it again. How they work together is simple. Engage puts the pushed back characters into a shared buffer. A character array Gauge reads from the buffer if there is anything there. It calls getChar if the buffer is empty. There must also be an index variable which records the position of the current character in the buffer. Since the buffer and the index are shared by Gauge and Engage and must retain their values between calls, they must be external to both routines. Thus we can write Gauge, Engage, and their shared variables as like this. We have used an array for the pushback rather than a single character, since the generality may come in handy later. Exercise 4, middle score 4, write a routine Engage, which will push back an entire string onto the input. Should Engage know about buff and BUFP, or should it just use Engage? Exercise 4, middle score 5. Suppose that there will never be more than one character of pushback. Modify Gauge and Engage accordingly. Exercise 4, middle score 6. Our Gauge and Engage do not handle a pushback EOF in a portable way. Decide what their properties ought to be if an EOF is pushed back. Then implement your design. 4.6 Static variables. Static variables are a third class of storage, in addition to the external and automatic that we have already made. Static variables may be either internal or external. Internal static variables are local to a particular function, just as automatic variables are, but unlike automatics, they remain in existence rather than coming and going each time the function is activated. This means that internal static variables provide a private, permanent storage in a function. Character strings that appear within a function, such as the arguments of printf, are internal static. An external static variable is known within the remainder of the source file in which it is declared, but not in any other file. External static thus provides a way to hide names like buff and buff in the Gauge and Gauge combination, which must be external so they can be shared, yet which should not be visible to users of Gauge and Engage, so there is no possibility of conflict. If the two routines and the two variables are compiled in one file then no other routine will be able to access buff and buff. In fact, they will not conflict with the same names in other files of the same program. Static storage, whether internal or external, is specified by prefixing the normal declaration with the word static. The variable is external if it is defined outside of any function. The internal if defined inside a function. Normally, functions are external objects. Their names are known globally. It is possible, however, for a function to be declared static. This makes its name unknown outside of the file in which it is declared. Instead, static connotes not only permanence, but also a degree of what might be called privacy. Internal static objects are known only inside one function. External static objects, variables, or functions are known only within the source file in which they appear, and their names do not interfere with variables or functions of the same name in other files. External static variables and functions provide a way to conceal data objects and any internal routines that manipulate them so that other routines and data cannot conflict even inadvertently. For example, get and engage from a module for character input and pushback, buff and buff up, and buff should be static so they are inaccessible from the outside. In the same way, push, pop, and clear form a module for stack manipulation VA1 and ESP should also be external static. 4.7 Register variables. The fourth and final storage class is called register. A register declaration advises the compiler that the variable in question will be heavily used. When possible, register variables are placed in machine registers, which may result in smaller and faster programs. The register declaration looks like, and so on. The end part may be emptied. Register can only be applied to automatic variables and to the formal parameters of a function. In this later case, the declaration looks like. In practice, there are some restrictions on register variables reflecting the realities of underlying hardware. Only a few variables in each function may be kept in registers, and only certain types are allowed. The word register is ignored for excess or disallowed declarations, and it is not possible to take the address of a register variable, a topic to be covered in Chapter 5. The specific restrictions vary from machine to machine. As an example, on the PDB-11, only the first 3 register declarations in a function are effective, and the types must be in char or pointer. 4.8 Block structure. C is not a block structured language in the sense of P, else/I, or argle, in that functions may not be defined within other functions. On the other hand, variables can be defined in a block structured fashion. Declarations of variables, including initializations, may follow the left brace that introduces any compound statement, not just the one that begins a function. Variables declared in this way supersede any identically named variables in outer blocks and remain in existence until the matching right brace. For example, in the scope of the variable I is the true branch of the if. The I is unrelated to any other I in the program. Blocking structure also applies to external variables. Given the declarations, then within the function f, occurrences of x refer to the internal double variable. Outside of f, they refer to the external integer. The same is true of the names of formal parameters. Within the function f, z refers to the formal parameter, not the external. 4.9 Initialization. Initialization has been mentioned in passing many times so far, but always peripherally to some other topic. This section summarizes some of the rules now that we have discussed the various storage classes. In the absence of explicit initialization, external and static variables are guaranteed to be initialized to 0. Automatic and register variables have undefined values. Simple variables, not arrays or structures, may be initialized when they are declared by following the name with an equal sign in a constant expression. For external and static variables, the initialization is done once, conceptually at compile time. For automatic and register variables, it is done each time the function or block is entered. For automatic and register variables, the initializer is not restricted to being a constant. It may in fact be any valid expression involving previously defined values, even function calls. For example, the initializations of the binary search program in Chapter 3 could be written as instead of. In effect, initializations of automatic variables are just a shorthand for assignment statements, which form to prefer is largely a matter of taste. We have generally used explicit assignments because initializers in declarations are harder to see. Automatic arrays may not be initialized. External and static arrays may be initialized by following the declaration with a list of initializers enclosed in braces and separated by commas. For example, the character counting program of Chapter 1, which began, can be written instead as. These initializations are actually necessary since all are 0, but it is good form to make them explicit anyway. If there are fewer initializers than the specified size, the others will be 0. It is an error to have too many initializers. Regrettably, there is no way to specify a repetition of an initializer, nor to initialize an element in the middle of an array without supplying all the intervening values as well. Character arrays are a special case of initialization. A string may be used instead of the braces and commas notation. This is a shorthand for the longer but equivalent. When the size of an array of any type is emptied, the compiler will compute the length by counting the initializers. In this specific case, the size is 4, 3 characters plus the terminating \0. 4.10 Recursion. C functions may be used recursively, that is, a function may call itself either directly or indirectly. One traditional example involves printing a number as a character string. As we mentioned before, the digits are generated in the wrong order. Low-order digits are available before high-order digits, but they have to be printed the other way around. There are two solutions to this problem. One is to store the digits in an array as they are generated, then print them in the reverse order, as we did in Chapter 3 with I to A. The first version of printd follows this pattern. Printd. The alternative is a recursive solution in which each call of printd first calls itself to cope with any leading digits, then prints the trailing digit. When a function calls itself recursively, Each invocation gets a fresh set of all the automatic variables, quite independent of the previous set. Thus, in printd parentheses 1 to 3, the first printd has n equal 1 to 3. It passes 1, 2 to a second printd, then prints 3 when that one returns. In the same way, the second printd passes 1 to a third, which prints it, then prints 2. Recursion generally provides no saving storage, since somewhere a stack of the values being processed has to be maintained, nor will it be faster. But recursive code is more compact and often much easier to write and understand. Recursion is especially convenient for recursively defined data structures like trees. We will see a nice example in Chapter 6. Exercise for middle score 7. Adapt the ideas of printd to write a recursive version of I to A. That is, convert an integer into a string with a recursive routine. Exercise for middle score 8. Write a recursive version of the function refers, which reverses a string S. 4.11. The C preprocessor. The C preprocessor. C provides certain language extensions by means of a simple macro preprocessor. The hash defining capability which we have used is the most common of these extensions. Another is the ability to include the contents of other files during compilation, file inclusion, to facilitate handling collections of hash defining handling collections of hash defines and declarations, among other things. C provides a file inclusion feature. Any line that looks like is replaced by the contents of the file name. The quotes are mandatory. A file 9 or 2 of this form appears at the beginning of each source file. To include common hash defining statements and external declarations for global variables. Hash include is maybe nested. Hash include is the preferred way to tie the declarations together for a large program. It guarantees that all the source files will be supplied with the same definitions and variable declarations, and thus eliminates a particular nasty kind of bug. Of course, when the included file is changed, all files that depend on it must be recompiled. Macro substitution. Macro substitution. A definition of the form hash definition yes1 calls for a macro substitution calls for a macro substitution of the simplest kind, replacing a name by a string of characters. Names in hash define has the same form as the identifiers. The replacement text is arbitrary. Normally, the replacement text is the rest of the line. A long definition may be continued by placing a backslash at the end of the line To be continued. The scope of a name defined with the hash define is from its point of definition to the end of the source file. Names may be defined. Names may be redefined, and a definition may use previous definitions. Substitutions do not take place within quoted strings. So, for example, if yes is a defined name, there would be no substitution in printf yes. Since the implementation of hash define is a macro prepass, not part of the compiler proper, there are very few grammatical restrictions on what can be defined. For example, orthographians can say and then write like this. It is also possible to define macros with arguments, so the replacement text depends on the way the macro is called. As an example, define a macro called max like this. Now the line will be replaced by the line like this. This provides a maximum function that expands into inline code rather than a function call. So long as the arguments are treated consistently, this macro will serve for any data type. There's no need for different kinds of max for different data types, as there would be with functions. Of course, if you examine the expansion of max above, you will notice some pitfalls. The expressions are evaluated twice. This is bad if they involve side effects like function calls and increment operators. Some care has to be taken with parentheses to make sure the order of evaluation is preserved. Consider the macro. One invoked as core parentheses z plus 1. There are even some purely lexical problems. There can be no space between the macro name and the left parenthesis that introduces its argument list. Nonetheless, macros are quite valuable. One practical example is the standard i/o library to be described in Chapter 7, in which getchar and putchar are defined as macros. Obviously, putchar needs an argument, thus avoiding the overhead of a function call per character processed. Other capabilities of the macro processor are described in Appendix A. Exercise 4 mid-score line define a macro swap parentheses x, y, which interchanges its two int arguments. Block structure will help. Chapter 5. Pointers and arrays. A pointer is a variable that contains the address of another variable. Pointers are very much used in C, partly because they are sometimes the only way to express computation, and partly because they usually lead to more compact and efficient code than can be obtained in other ways. Pointers have been named with the goto statement as a marvelous way to create impossible to understand programs. This is certainly true when they are used carelessly, and it is easy to create pointers that point somewhere unexpected. With discipline, however, pointers can also be used to achieve clarity and simplicity. This is the aspect that we will try to illustrate. 5.1 Pointers and addresses. Since a pointer contains the address of an object, it is possible to access the object indirectly through the pointer. Suppose that x is a variable, say an int, and that px is a pointer created in some as yet unspecified way. The unary operator ampersand gives the address of an object, so the statement px equal ampersand x assigns the address of x to the variable px. Px is now set to point to x. The ampersand operator can be applied only to variables and array elements. Constructs like ampersand parentheses x plus 1 and ampersand 3 are illegal. It is also illegal to take the address of a register variable. The unary operator asterisk treats its operand as the address of the ultimate target and accesses that address to fetch the contents. Thus, if y is also an int, y equal asterisk px assigns to y the contents of whatever px points to, so the sequence assigns the same value to y as does. It is also necessary to declare the variables that participate in all of these. The declaration of x and y is what we've seen all along. The declaration of the pointer px is new. Is intended as a mnemonic. It says that the combination asterisk px is an int. That is, if px occurs in the context asterisk px, it is equivalent to a variable of type int. In effect, the syntax of the declaration by variable mimics the syntax of expressions in which the variable might appear. The reasoning is useful in all cases involving complicated declarations. For example, say that in expression a to f parentheses and asterisk dp have values of type double. You should also note the implication in the declaration that a pointer is constrained to point to a particular kind of object. Pointers can occur in expressions. For example, if px points to the integer x, then asterisk px can occur in any context where x could sets y to 1 more than x, prints the current value of x, and produces in D the square root of x, which is coursed into a double before being passed to squared. In expressions like the unary operators asterisk and ampersand bind more tightly than arithmetic operators. So this expression takes whatever px points at address 1 and assigns it to y. We will return shortly to what y equal asterisk parentheses px plus 1 might mean. Pointer references can also occur on the left side of assignments. If px points to x, then asterisk px equals 0. Sets x to 0 and asterisk px plus equal 1 increments it as does. The parentheses are necessary in this last example. Without them, the expression would increment px instead of what it points to, because unary operators like asterisk and plus plus are evaluated right to left. Finally, since pointers are variables, they can be manipulated its other variables keep. If py is another pointer to int, then py equal px copies the contents of px into py, thus making py point to whatever px points to. 5.2 Pointers and function arguments. Since C passes arguments to functions by call by value, there is no direct way for the called functions to alter a variable in the calling function. What do you do if you really have to change an ordinary argument? For example, a sorting routine may exchange two out-of-order elements with a function called swap. It is not enough to write where the swap function is defined as like this. Because of call by value, swap can't affect the arguments A and B in the routine that called it. Fortunately, there's a way to obtain the desired effect. The calling program passes pointers to the values to be changed. Since the pointer &give is the address of a variable, &a is a pointer to A. In swap itself, the arguments are declared to be pointers, and the actual operands are accessed through them. Okay, fine, guys. It's time for me to take a break. Goodbye.